Well, first, thanks for having me here give the keynote. I'm very much honored by the privilege. And it's great to be finally here at the JVM Language Summit after, for so many years, I just couldn't make it because it was always during vacation season in Europe. Now we decided we do vacation in California, so that's what we did, and I can come to the summit. Great. So you might say, well, that's really a shameless thing for Oracle to say, well, since Oracle is a database company, now this guy is claiming that compilers are databases just to suck up to Oracle. So no, it's not that. In fact, compilers, I've come to realize, are very much like databases, and I hope that in my talk I will explain a little bit why that's a valid mode of thinking. So if you look at compilers, then a compiler is essentially, that's the standard picture. If you look on Google image search, that's the first thing that pops up probably. So a compiler is a source program. It translates into an executable program, and that thing then can be run. In a database, we all know it's this big round thing, right? So that's the thing. So this thing looks pretty square, and this thing looks pretty round. So aren't we putting a square peg into a round hole, or vice versa? Well, we'll see. So in this talk, what I'm going to do is I'm going to report on a new compiler architecture for the Dotty compiler, Dotty Scala compiler that I've been working on over the last 2 years, a little bit more than 2 years now. And that compiler has a mostly functional architecture, which is a new thing. Typically, with compilers, you say, well, a compiler is not allowed to use any of the goodies that the language provides. It typically is written in a very low-level language like C, or it's written in Java, but typically you don't make use of any of the high-level things because compilers have to be fast. And so essentially, you do all this for everybody else, but you can't partake of it. So that we have changed here. So now essentially the compiler tries to use all of the functional goodies that we have in the language. And it turns out that some of the concepts in the compiler are very much inspired by databases, and in this case, I mean functional databases. So I've been essentially a compiler guy for all my life. I started in the 80s. I wrote a Pascal compiler that got bootstrapped on an Osborne 1, 52 kilobytes of memory. First version was in assembly code because the only freely available language at the time was BASIC, and that was unusable. So we wrote it in assembly, and then we bootstrapped Pascal, Mini Pascal to Micro Pascal, Mini Pascal, Full Pascal, and that became modular 2. And those compilers were all essentially very fast single-pass compilers, pretty much actually like the Go compiler. And I think it's no coincidence that actually one of my colleagues in the group of Niklaus Wirth, Robert Griersamer, he's now one of the core members of the Go team. So there you see sort of the genes spreading around. So then in the 90s, I wrote a Java compiler called Espresso. And that compiler actually became the basis of the E language, which is a very interesting language in its own right, that essentially is vaguely Java-based. And it also became the compiler of Borland's JBuilder. So that used essentially a very object-oriented approach, where at the time, object orientation was all new and shiny, so everybody had to do this. So the conventional wisdom was, well, you should have an AST, and it has like 40-ish classes for the different kinds of nodes. And essentially, every node is a class, and we put all the methods in the class, because that was the object-oriented dogma. So essentially, you would have 40 methods to type check, 40 methods to do flow analysis, 40 methods to do pretty printing, 40 methods to have code generation. And of course, it was all a huge mess, because logic was spread out in each case over 40 classes. So that we learned to do better than in the next compiler architecture that started with the Pizza language in the 90s. That became GJ, and that became Java-C from essentially 1.3 on. And that became then, in the end, Scala C, the first Scala C used a very similar architecture. So first Scala C was actually written in a dialect of Java, which was sort of like Pizza. Somebody else wrote it, so it wasn't exactly Pizza, but it was Java plus pattern matching, because pattern matching is just too good not to have when you write compilers. but otherwise it was basically Java, and we wrote Scala C in that Java. So then from 2004 on, we had the second Scala compiler, which is still the workhorse that everybody's using for Scala. That's called NSC, for New Scala Compiler. At the time it was new. And that essentially was written in Scala from the ground up, and it made use of some of the functional capabilities of Scala. Not that much, I have to say, because speed is important, and we didn't really trust the functional abstractions to be fast enough at the time. So over the time, this thing grew a lot. So the first thing we added was a REPL. Then we added essentially the presentation compiler interface for IDEs, so the Eclipse IDE, and I think also the NetBeans IDE and the Enzyme plugin for essentially editors, all uses essentially the standard Scala compiler to do essentially the editing help. And then in 2010, there came the macros, and there were the toolboxes essentially where you could interact with the compiler at runtime. And that's the code base for the official Scala C compiler for the current version 2.11 and also the next version 2.12. So what I have been working on for the last 2.5 years was now essentially a new compiler base where the project name is called Dotty. And the idea there was we wanted to rethink compiler architecture from the ground up and also introduce some language changes with the aim of better regularity. So we're currently close to Bootstrap, but the whole thing is still rough around the edges, so it's not really production quality yet. So what I'm going to talk now is essentially what came out of the thinking of the architecture of this compiler. So a traditional view of a compiler is it's essentially a pipe. It's a transformer that takes source programs to output programs. Classical function, you could say. It takes an input, produces an output. And well, of course, typically you have several sources. And if you add separate compilation, then the picture becomes a little bit more complicated. So the compiler doesn't just produce the output, the byte codes or the assembly code, but also essentially some symbol table information that then gets fed into as an input when you do separate compilation. So essentially for every one of these symbol table things, essentially gives you the API of a separately compiled file, and these get fed into the compiler. But basically, it's still a transformer. It takes inputs and produces outputs. So the challenges in this view is that a compiler for language like Scala is actually rather hard to write. So there are quite a few challenges. The most important are these things get complex. The other challenge is we want the compiler to have reasonably high speed, and that's very hard to achieve. We want it to be fast in the latency. That means for a REPL or for a presentation compiler, it's important that you get the that you get the output in a split second. And we also need to use the same compiler code base in a number of different systems. So we want to have this code base be reusable for many different applications. So complexity. Well, the complexity, you could say, well, is that inherent, or did you just maneuver yourself into essentially a hole here? Well, I think it's to a large degree inherent that a compiler for a complex input language like Scala is also a complex thing. So the input language Scala is complicated, but when I say that, I would say, well, essentially, it's not fundamentally different than, let's say, Java 8. Java 8 is by now also a fairly complicated input language, and I guess Kotlin would be a fairly complicated input languages. These things are not like simple academic languages which you can describe on a page. They have a lot of real-world concerns. The next problem is that the output language, the JVM, is also complicated. So you have essentially a complicated input language, a complicated output language, and for Java, the saving grace is the two are not that different. Java and the JVM are essentially developed in lockstep, and so essentially a lot of the things that the language needs, the JVM will provide. Whereas for Scala, that's not true. There's a huge semantic gap between what Scala is and what the JVM is. We can bridge it, but we require a lot of transformations. So that means that we have essentially a complicated system that requires a lot of different transformations to map into another complicated system. If you compare to, let's say, simple low-level languages like SystemF or SSA, they have it much, much easier. So for instance, the Haskell language is also a complicated language. The type checker is quite subtle and complicated. But once they're done, they map into essentially SystemF plus constraints. And that's a very simple intermediate language, which is much more malleable than what we have to do. So we can't map into that, of course, because then we cannot recover the high-level information when we want to map into the JVM and be interoperable with Java. That's why we have to stay essentially on the complex high level all the time. So the next reason why it's complicated is that there's a very, very deep transformation pipeline. So I don't know, for Java C right now, how many phases would there be between the type checker and the backend? I don't know. 5, 6. So that's a subset of the current system. So I think we have like 40. And they're bunched into macro phases, so they're fused typically, but conceptually there are 40 different things that have to happen here. So that's of course much harder to achieve good reliability. So to get good reliability here, you need excellent modularity, and also it should be clear now that you need to minimize side effects. So the nightmare bug is that a phase somewhere here introduces something fishy and things propagate, and then somewhere here things blow up. And you say, well, what's the reason for that? So how can we trace this back to where it was introduced? So you really need a lot of discipline to avoid that, and you need to essentially minimize the side effects and be able to test a lot of your post conditions. So for all that reason, it really would be very attractive to have a functional style, because functional code is known to be essentially much safer in that way. You can control your effects much better if you write things in a predominantly functional style. So then the next challenge was speed. So the current Scala C compiler achieves about 500 to 700 lines per second in idiomatic Scala code. If you write Scala like you write Java, you can get faster than that, but very few people do. If you write Scala like, let's say, shapeless, or if you write Scala like Haskell plus type level Haskell, then this count can drop dramatically. It can go down to, in one case, I saw a single line query that took 6 minutes to compile. Why? Well, it was a shapeless thing. So essentially, they have a very elaborate recursive implicit search. It's basically you write in Prolog, right? A single Prolog query can easily take 6 minutes. It can take 6 days to run, right? And implicit is basically gives you the same functionality as Prolog, and well, people use that. And so that was in particular essentially a way to write records in a statically type-safe way, so like database records. And all these things work fine if the record is maybe 5 columns and 10 columns, but people said, no, we want to use it for records with lots of columns, hundreds of columns, because that's what the real databases give us. And then, of course, well, there was some, I don't know, high polynomial or exponential factor, and it just blew up. So it just tells you, well, that's sort of the worst case. Normal Scala code doesn't have that. You get maybe 500 to 700 lines, but again, Java C is much faster than that. So we would rather want to be able to be, let's say, a factor of 5 faster than the 500, 700 lines. So everybody would like it to be faster, and it's very hard to achieve. So over the years, one of the graphs that I was most, I watched a lot, and it was very frustrating, was the build times. So the Scala C build times, so that's essentially the time that it takes Scala C to compile itself. And the graph looked pretty much like this. So it was an inclined plane, and there were some outliers when we did something stupid, so something that introduced much slower compile time, and then we corrected it and went back. But there was this background increase, which essentially happened because people introduced more and more of the, let's say, high-level nice features. So as people manage the code, they said, this is a while loop, this is a nasty, let's use a higher-order function instead, and things like that. And all these things have sort of a microscopic cost. So everything essentially adds up, and that led to these things. The other problem is that optimizations are singularly ineffective for compilers. If you've ever looked at spec marks, let's say Java-C, and you see Java-C is one of the spec mark benchmarks, then you see essentially all the optimizations that do something, sometimes something dramatic, for all the inputs, most of the inputs, except Java-C. Java-C never moves. No optimization is effective for Java-C. And I think that's not a thing for Java, that's not a property of Java-C alone, that's a property basically of all compilers. They don't really have hotspots. It's really all smeared out where the complexity goes. They're memory bound. It's not even clear whether they're memory bound or CPU bound. So that's why essentially most of the optimizations, or all the optimizations, all the simple ones I've seen, don't work for compilers. Okay, so the other challenge we're facing is latency. So some applications require not so much essentially baseline throughput performance, but very fast turnaround. So for instance, a REPL, you type a program line. The thing, what happens is after you type it, the thing gets compiled. The compiler spits out a class file representing the line. The class file gets executed, and all this should, of course, happen in a fraction of a second. Worksheet is basically like a REPL, just sort of a more two-dimensional layout, and then there's the presentation compiler for IDEs, which essentially has to do a lot of type checking for things like hyperlinking, command completion, and so on. So that means that all these things require to keep things loaded and not to have the compiler start from scratch. And the final challenge was reusability. So a compiler has nowadays many clients. It's no longer just a batch command. So you can use it from the command line, but it's also used from build tools, and build tools sometimes want to be smart about incremental compilation. It's used in IDEs, it's used in the REPL, it's used in metaprogramming. So that means that essentially the abstractions that a compiler provides, they must not leak. You want to have essentially a good API with which these essentially environments can interact with your compiler. Okay, so that's sort of the challenges that we want to face now, and come up with essentially some of the questions to ask for an architecture and some of the answers we had on these. So let's start with the first question. Every compiler has to answer a question, or questions like that. Say I have a class, C, parameterized class, and we have a method in the class called f. And at some point, we change the class to this one here. So now the method has two parameter lists. And the question I ask is, what's the signature of c.f? And clearly, the question is ill-formed, because the question should be, well, what's the signature at c.f at a given point in time, because I've just changed it. So, and it's not just changes that the programmer does, it's also changes that the compiler does, or transformations that the compiler does. So initially, this method f had this signature, xt to t. Now there's a phase in the compiler called erasure that exists also in Java-C that essentially maps down to the JVM model with essentially unreified types. So all the type variables get erased, and you get any to any. In Java, you would get object to object. After the edit, you have this curried function with two parameter lists. And there's a phase before erasure called uncurry that actually merges these parameter lists. So now you get one parameter list, and after erasure, you're back to this one here. So that the same name, f, in class C, has many, many different types, and some of them essentially change while the compiler is running, and the change from here to here was prompted by an edit of the user. So the naive functional approach would be to say, well, let's pick essentially all the functions in my world, all the classes, and just compile them with all these intermediate representations, of which there can be many, and we get the output. And then if we have a delta in the world, so we have an edit, then we have a new world, and we do the same thing again. The problem with that is that that world is essentially all the functions that you can get at. The world can be very large. The world can be as large as the internet is if you have transitive dependencies to jars that also can change in different projects and things like that. So the world can be humongous, and that's why this model is essentially not feasible. You can't use that as a basis of a compiler architecture. So a most practical strategy takes inspiration from functional databases in that case, and also functional reactive programming. The two are actually quite similar. And that idea is to say, well, we treat every value, like the signature of f, as a time-varying function. We just model it directly to say, well, if we want to take the signature of f, c.f, then we have to ask, well, at a given point in time, what is the signature of c.f? And remember, we want to be functional. Of course, if you were imperative, then, well, anytime you ask, you might get a different value. So that's not an issue. But we want to model this thing functionally. So what we then need to do is we need to index every piece of information with the time where it holds. So that's essentially our information space that you say, signature of c.f at a given period. So what is time? So time for us is essentially a pair of a run ID and a phase ID. So the run ID is essentially every time the compiler is run, it gets incremented. So you get one number for one counter for every time the compiler is run. And the second part of the time is the phase ID, that we say we have all these transformation phases, and the types can potentially change after each phase. So that's essentially the minor part of our period. So the phase ID runs from currently about maybe 1 to 50 or something like that. That's the phases we have. And the run ID is incremented on each compiler run. So that means that if we look at the signature of c.f now, then we have actually a well-defined function. We just essentially give it the run and the phase, and that would give you the signature that you've seen before. So at run 1 in phase parser, you would have that. At phase erasure, you would have that. At run 2, you would have that, and so on. So the task of the compiler then is to compute all values needed for analysis and code generation over all periods where they're relevant. That's simple enough. But again, of course, the problem is I've just reformulated the problem statement. The graph of this function is, again, humongous. So it's just like essentially taking the world and recompiling it every time. I just essentially have sliced and diced things slightly differently. So the graph is very big, so we need more work to make that efficiently explorable. But for a start, it looks like the right model. So it looks like a high-level model that really models what goes on here. So what I'm going to do now is look at some of the core data types of a compiler and how they relate to this model. So the types I'm looking at will be abstract syntax trees, types, then something called references, something called denotations, and something called symbols. And in traditional compilers, I think you recognize abstract syntax trees. They all have that, basically. You recognize types, of course. They all have that. And you recognize symbols. But these things, they probably require some more explanation. So let's look at abstract syntax trees first. So here we have a simple abstract syntax tree for an expression like x times 2. So that would be an apply node, a function application. Well, in Scala, I should say that's x dot star is a method name and 2 is the argument. So it's an apply node. The left hand, the function of the apply node is a selection of x on the star on the identifier x. And the argument of the apply node is a list that consists of the single argument, which is a literal and the number 2 of the literal of the number 2. Okay, so that's the simple abstract syntax tree, and I know that, of course, various ways to write that, but they're all essentially equivalent to something like that. But these are sort of the things that you get from the parser. Once the compiler gets going, more things have to be added. So we have to put typically attributes in this tree. So what attributes do these trees carry? And in DSC, we've simplified that as much as we could. and we're just left with 2 attributes in the tree. So every tree node has exactly 2 attributes. One is its position, so it's essentially start position, end position that you need for error reporting and the IDE work, and that's intrinsic. So it means the parser generates that already for us. And the other is the type, and the type needs to be computed by the type checker. And that's it. So there are no other attributes, there are no symbols or anything else. So the job of the type checker then is to transform untyped trees into typed trees. So type tree would like look something like that. So we would say for each node, we essentially add the type, which is done here in red. So let's say the identifier x is determined to be of type int. Then the select node would be of type with the star int to int. The literal is of type constant type 2, which is known to be a subtype of int. And then the application is again of type int. So in the current Scala C, we didn't distinguish untyped from typed trees. So a tree was essentially just had a variable, which was this type attribute, and that got set by the type checker. And in retrospect, I think that was a big mistake, in particular for reusability, because the distinction whether the tree holds a type or doesn't is actually quite fundamental. So it's very important to know this tree is typed or it's untyped. So in DSC, we made an effort to actually distinguish typed from untyped trees in the type of the tree itself. So what we did here is we said, well, let's give a parameter, a type parameter to the tree type. And the type parameter tells you what kind of attribute it holds. So a type tree holds a type, so it's a tree of type. An untyped tree holds nothing, so it's a tree of nothing. So we have this very cute nothing type, which is the bottom type, which says, well, there's nothing there. If you try to get anything, you get an exception or non-termination or whatever. So that leads to the following class. We have essentially the base type of all nodes in the AST is type tree of T, where we can get the type out, and it will give us a T, either type or nothing. And then there's a method with type, which is essentially called by the type checker, and the type checker essentially gives it a type, and then we get out a tree of type. And there's actually a clever copy on write strategy that we say, well, if we start with an untyped type and untyped tree, and we haven't given it a type yet, then the first time we give it a type, essentially we don't need to create a new node. We can just reuse the old node, but then if somebody gives it a new type, because the context it's used in a different context, say, then you will copy the tree at that point. Okay. And so now we actually have an interesting question of variance. So Scala has declaration side variance. For Java C, the problem would be slightly different. It would be essentially where do you put the extends and the super. So essentially, how should you use these trees? So the question is, what's the right variance of this type parameter T? Here I've declared it to be non-variant, but maybe that's not the best choice. Well, if we look at usages, which of the two would be more useful? A typed tree is also an untyped tree, or an untyped tree is a typed tree? What would you think? Well, I would claim it's this one here. So going from type to untyped just means forget about the types. Just use the basic structure, retype check it again. So I can always forget types. But going from an untyped tree and just assuming it has a types just doesn't seem to be sound, right? So it should be the first. On the other hand, what relationships do the variance rule here imply? Well, the variance rules say, well, it appears covariantly, right? So that's a result. So that must be a plus here, covariant. But covariant would mean that because untyped is nothing, it would mean that. So a tree of nothing is a subtype of a tree of type because nothing is a subtype of type. Interesting. So it seems our variance checking has hit a problem here. So let's try to resolve that. So I first resolve it just with a big hammer. I put unchecked variance here and say, okay, I'm done. I say, well, it's contravariant because that's the more useful relationship, and I put unchecked variance here. If I put unchecked variance here, of course, it means I'm unsound, right? So I just say I'm smarter than the type checker is. So how am I smarter? What could go wrong if I write this? So what can go wrong here is that given an untyped tree, I take its type, and I think I will get a nothing, but in fact it gives me a type. That's the only thing that can go wrong. But if I think I can get a nothing, what happens? There is no value of type nothing. That means I'm calling for an exception to be called. And well, it doesn't give me the exception, it gives me actually something nice, which is a type. So that seems to be a quite benign unsoundness in that case. So I think we can live with that. And that's actually interesting because it shows that having an escape hatch for essentially any sort of hard typing rule is actually very important, because there are surprising situations like this where you say, well, no, a type system wouldn't have thought of that. And it's actually pretty good to give the compiler enough, to give the compiler writer enough wiggle room to convince the language that the rules are still okay here. Okay, so let's go on. So types carry most of the essential information of trees and symbols, and there are two kinds of types. There are the value types that are the types of expressions like int or int-to-int or the pair of Boolean and strings. And then there are types of definitions like that's a signature of a method, that's the lower and upper bound of an abstract type, or the information of a class. And they're represented as the subtypes of the same type just for convenience. So then the next thing is references. So here we have two abstract syntax tree classes. They're both extend tree. One is called select and the other is called ident, and they do essentially the usual thing, an identifier or a selection. So what should their types be? Normally, in Java C and the current Scala C and basically all compilers I know of, these things would have a symbol attribute. I would say, well, I point to a given symbol and I pull the type out of the symbol. But we don't have a symbol attribute for good reasons. So what should its type be? Well, the traditional scheme in a compiler is to say, well, we have this transformation, and then there's the symbol table, which essentially stores the value of all symbols. And then we essentially put stuff in there and pull things out. But it's not very functional. And we've already seen the thing is actually quite complex because the types of these symbols, they also change all the time. So the question then is, if we have, let's say, a selection like object.function, what's its meaning? The type will be part of the meaning, but what's its meaning? And the answer, of course, is, well, it depends on the period. It depends on when you ask that question. That's what we started with. So does that mean that object.fun, the tree object.fun, has different types depending on the period? No, we want to be functional. Trees should be immutable. So once we have a type, the type shouldn't change. So what can we do there? So what we do is we introduce references, which are essentially a subclass of type. And there are two kinds of references, to terms and to types. And they both share a common superclass called named type. And that type has, as its only attributes, a prefix, potentially, which can be a type or no prefix, and a name. So a reference is just the name, basically, and the thing on which you select. That's all there is. And then here you have these subclasses for term refs and type refs. Okay. And furthermore, references are immutable. They exist forever. So I can say, well, the thing called f in class C, and that's a valid reference for all periods of time. It could have different meanings, but the reference is the same. Now, if you're a compiler writer, you will immediately come up with this question, what about overloads? So if you reference a term, like a method, then it can be shared by several overloaded, the name can be shared by several overloaded members of the class. So how do we determine which member is meant? If you have a symbol, that's easy. Each of these members will have a different symbol. We just point to the symbol. But I just said we don't want to have symbols. We have these references only. In a nutshell, that question is why overloading is so universally hated by compiler writers. That's really what makes things messy. The trick we use here is that we essentially allow the signature of things as part of the term name. So essentially, we encode the erase type, sort of what the JVM does. It's essentially, as a term name, we add the signature, and that will disambiguate overloaded methods and overloaded names. Okay, so then we say, okay, we have these immutable references. What do they reference? Well, you could say, well, surely now it's a symbol, right? A reference gives me a symbol. Well, actually, no, it's still wrong, because references actually capture more than a symbol. So the meaning of a reference is more than a single symbol, and sometimes they don't refer to a single symbol at all. So it's neither a subset nor a superset. It's still disjoint from symbols. So let's look at these things. References capture more than a symbol. So here we have a case of a class C, again the method f, and we have a prefix, and we say, well, create a new value of C of int. So now we have C of int. Now, the reference prefix .f, right, it will resolve to this method f, but we also need to know that the type that we resolve to is here a method int to int, not t to t. T to t wouldn't even be legal because t is local to the class C. So we can't have a reference resolved to that type. So with the reference, we actually need to carry the particular type of the reference, which is not the same as the type of the method. That's a Scala C, again, didn't do that, this modeling with references, and it's the most common rookie mistake of compiler writers in Scala C to just say, well, we have a reference to a symbol, we just pick the type of the symbol. Bzz, no, wrong, it's not. The bad thing is it works in simple cases. As soon as things get parameterized and generic and complex, it falls apart. So very easy mistake to make. So the right modeling then is that both of these pieces of information are part of the meaning of prefix.f. The other side of the coin is sometimes references point to no symbol at all. Here's an example using union types, which are newly supported by the compiler and will be in a future version of Scala. So we would have two classes, and they both have this method f. And then we have a prefix, and it's now A or B. We don't know which it is. It's one or the other. And the two classes, they don't have a common superclass except object. And we return either one or the other. Then the question is prefix.f, what definition does it refer to? And the answer is we don't know. It could be either one. So again, the reference is not tied to a symbol. Okay, so what does it mean then? So, well, we just say, well, we introduce a new thing. So a reference denotes something. So the thing it denotes is obviously a denotation. So that's how we named it. So a denotation then is either a multi-denotation, that means it's overloaded, we don't know yet which ones, or it's a single denotation, and then it might have a symbol and it always has a type. And then there's a subclass of single denotation called sim denotation, which says, well, in some cases, actually, I do have a single symbol, and that's what the symbol is. So what then is a symbol? So a symbol represents a declaration in some source file, right? So it's what I write in some source file, what the compiler extracts from that. And the symbol lives as long as the source file is unchanged. So symbols actually have lifespans. The other things haven't. So the other things are immutable, but a symbol has a lifespan. And symbols have denotations, again, and that depend on the period. So in particular, the compiler phases. Okay, so then the question is, well, if we have these denotations, and the compiler then goes forward to different phases and edits, how do we compute the new denotations from the old ones? So if we have a reference pre.f, then we can just recompute the member at the new phase. But for a symbol, how do we do that? So a symbol has a meaning, and then we transform it, and then it will have a different meaning. If all my symbols were parts of trees, it would be simple. I would just transform the tree, and I would get essentially the new tree, and that would give me the new information. But that's not the case. The symbol can come from any jar, and these jars have a high-level information, and then that information gets changed. So again, I don't want to essentially do that for the whole world. So what I need to do instead is essentially when I use a symbol, I want to be lazy and say when I use a symbol, I want to be able to compute its meaning at a given period from what it had when it was loaded. So what I need in each phase then is essentially two methods. One is the tree transformer, transforms one tree to another. It essentially gives me the transformed trees. And the other is the denotation transformer, which says I give it a symbol and it says its type was that before your phase, what is its type afterwards? So for instance, in the uncurry phase, the transdenote transformer would say, well, if a symbol has this type, then afterwards it will have this type. Okay, So now we're getting to some bigger images. So the symbol here then, what a symbol is it has a bunch of denotations which depend on the phase. And these denotations are computed from, essentially that's the first one on phase 1, 2, 3 with these transdenote things. And they're stored so that if ever I come back to a previous phase or I want to know the meaning several times, they're cached. So they're cached in essentially a ring here. And a symbol essentially just has a pointer to what its last denotation was. And that tells me essentially where we were. And then if we want to go to a denotation in a new phase, then I will essentially apply these transformers as needed. Or if it's already in the ring, I will just pull it out here. So symbols are essentially functions from period to denotation. And here, essentially, since I store that, they're memorized functions. There's an efficient caching strategy to memorize them. OK. So putting it all together, what we've seen, since I argued that compilers are databases, I need to give you an entity relationship diagram, of course, because that's what people with databases do. But actually, it's very instructive for the compiler as well to look at that. So we've seen the trees. They're over here, and they have this single attribute called type. Position we ignore, that's trivial. So a type, then, the variety of types, but the important one is there are these name types, which are the references. And the name types, they now have a denotation, but that denotation is time varying. So a name type can point to different denotations according to the phase of the compiler and according to the edits of the user. So both of these things can affect that thing. So that's essentially, the denotation is indexed by the P, where P is this period. So that's important that this is time varying, whereas all the other things are constant, they're immutable. So a denotation then has always an info, which is again a type. And it can be a single denotation or a multi-denotation. If it's a multi-denotation, then essentially each denotation gives me a part of one of the symbols in the overloaded family of symbols. If it's a single denotation, then it has potentially a symbol, might not have, but some of them do. And a symbol then points again to a denotation, which is the current denotation of the symbol. And again, that thing is time varying. So that thing has to be efficiently recomputed. So now you have it. So what I've done here is essentially to say, well, traditionally, compilers are these big machines that lots of moving parts, things change all the time. And if you say, well, no, let's not do that. Let's freeze. Let's be completely functional. Let's have something like essentially an immutable database, time-varying database. What are the pieces that really have to be indexed by time? And that's that one and that one. All the rest we can keep constant. So lessons learned. We're not done yet. We're still learning. I think databases for modeling, it's a good idea. A lot of things were learned for the database community. FP for transformations is also a good idea. And then the question is how to get the efficiency. There, on the one hand, you pay a price with functional. On the other hand, there's lots of opportunities, because once you are purely functional, you have much more, once you're functional, you have much more opportunities for caching, because you know that essentially once you've computed the value, the next time you compute the value, it's the same time. It's the same value. Whereas otherwise, if you have lots of imperative moving parts, essentially caching is unfeasible, because you never know whether the next time you ask that question, it might depend on something that has changed in the meantime. So that's why essentially functional gives you a lot of opportunities for getting better efficiency through mostly caching. So the idea is think FP for transformations, use caching to get the efficiency, but take care not to compromise the high-level semantics. So to find out more, so there's a project called Dotty. You can go to the web page and see what's going on currently. I don't know how much time I have.
Plenty of time.
I've got plenty of time. OK, I can go to some of the supplement slides, how to make it fast. So first, I should say we don't really have definitive speed numbers yet. So I don't know how fast it is. It's hopefully faster than the current Scala C compiler. I don't know right now by how much, because we haven't taken out the training wheels. So there's a lot of instrumentation that slows it down and things like that. So we'd have to take that out and then measure. But we haven't done that yet. So to make it fast, For symbols, we've already seen that. They cache the last denotation. So essentially, if to say, well, what does this symbol mean? You just essentially go through the cache and say, well, what is it still valid? Then take it. For name types, it's the same. They cache the last denotations. These caches, they're stamped essentially with the validity interval. A validity interval is essentially two IDs. Well, it's always a single run ID, and then essentially two phases. It's valid from this phase to that phase. And if it's outside the validity period, then you need to update, but not otherwise. The other thing we do is that if you want to find, to get the member, so something like this. So where we say, okay, prefix.f, that's of course a very common operation that you say, well, take the member of a thing at a certain, with a certain prefix, what's its type? And then essentially you have to always come back with two pieces of information, namely essentially the symbol, if it has one, and the type. So the naive thing would be you create a new object every time you ask a member operation, and that can be very costly because member operations are done all the time internally by the compiler. So what we actually do is we have a least recently used cache of these things. So we say, well, given a prefix, we store the last 8 members or so that were asked for, and we essentially give you back the type immediately. So some of the same techniques which probably JITs would also do. And it also turns out here, I'm saying that because I want to, impress on you. Let me just put this on electricity, because otherwise we'll be cut short. Okay. So I'm saying that to just impress on you that caching is not something that can be done completely automatically, like function memoization in functional languages or just lazy values or things like that. No, it's pretty much an art to pick the right cache for the right problem. And sometimes you have to do things like least recently used caches, which definitely you have to do manually. No language will give you that automatically. Okay, so caches then are lazy vals memorizations, LRU caches, and they rely on essentially the purely functional semantics and access to, but in a sense, you can have this only if your language, or if your architecture is predominantly purely functional, but you still need access to the low-level imperative implementations to implement your caches. And that's sort of the nice thing, what I like most is sort of to be in between those two levels. So to do really very sophisticated imperative code to get a very clean high-level functional semantics over there. And I very much value a language that lets me do both of these things. It's of course important to keep the levels of abstractions apart. So you need to, once you do that, you need to be very sure that you implement a consistent high-level model, because if it leaks out, then essentially all chaos will ensue. You will have essentially something that is unpredictable at any level. There's a lot of magic and there's a lot of hidden things, so leaky abstractions would be terrible in this thing. And of course, it would be nice to have better language support to keep those abstractions apart. Scala doesn't have them, so in Scala, essentially, we rely on discipline, programming, the discipline and conventions to keep them apart, certain maturity of the programmers, in a sense. It would be nice to have something more, but as long as we are not very sure what we want to add, we won't add anything in that department. Another idea that helps a lot is, I've shown you these phases, like 50 phases. So it actually turns out that a lot of the performance problems of a compiler stem from memory locality. So if you have a large program, then your trees won't fit in any cache, so they will definitely be in main memory. And if your transformation pattern is essentially full tree traversal, generate new tree, essentially you have cache misses all along. So that's very bad. So one way you can remove that or lower that cost is by having larger phases. Phases do more things, but that means you give up modularity. So these phases now essentially are a grab bag of features, and it's very hard then to argue what they do. So what we did is essentially we solved that architecturally. So we have many phases, but we essentially have an automatic fusion phase. So essentially a phase registered on what nodes they do any transformations, and then you have a reflection-based fusion framework where you can put many phases into a group, and all these phases will then be applied together in a single tree traversal. But you can essentially simply move phases from one group to the next with a single edit from one on a single list, and it will just refuse automatically. So that was a big win in performance, because we have essentially overall we have I think five groups, which brings us back to essentially Java C's thing, 5 or 6 groups, something like that. But we have many more phases in those groups. Okay, that's it. That's all I had. So if you have more time, then of course happy to answer questions.
See this taken further, and maybe you've already taken further. One of the reasons why you put data in a database is so that multiple clients can access the data independently without me having to ask you as the data priest to go do a query operation for me. And so, in this model, you have almost all of your immutative transactions against the database are being generated by the compiler, but then you have clients like the IDE that are doing read-only queries against the database. And so, where I hope you're going with this is that by actually presenting a functional database view of your program that captures the whole history of the program edits, then the IDE can just operate on that and doesn't have to get the compiler involved if new code transactions are not being put into the database. Is that sort of where you're going, or
yeah,
pushing the analogy too far?
I don't know. So for me, the source of the data, so the raw data is just essentially the versions of the source code. So think Git somewhere. So version control system. That's where it starts from. So essentially, all the compiler does is view management. So you say, well, the truth is always in the source, but I want to get essentially a different view on this thing, like what are the types which require complex calculations, and that's the job of the compiler, to essentially do view management on a database, which is essentially a version control system. So I'm not sure. I think it's probably very similar to what you wanted, or do you think the differences?
Well, I guess the question is this applying the notions of database to the internals of the compiler, or is this taking it further where there actually is a database in quotes, that the compiler is putting transactions into the database, and somebody else can query the database without having to have the compiler be involved, like the IDE or the reference.
Right, so essentially the question is, do we persist those views in the database? So right now, no. So we compute them on the fly. We could, I guess, but I haven't thought about that yet. Yeah. Yes?
And like in a REPL or something, as people do execution, that's sort of part of the whole flow process. You're compiling, executing, compiling. Would it make sense for that execution to be a phase or like a run in that too, so you could back up and go forward, or is that too much?
That would depend on your inputs, whether your inputs are also essentially persistent, and then I guess you could take it further. Yeah. Yes.
It's maybe a follow-up to Brian's question. So you have those run IDs, right? That doesn't mean that you're like incremental inherently. But how do you know what to invalidate? Like how much you have to recompute when the run ID is different anyway?
So right. So this is not yet. So this needs to be augmented to be a full build system, where essentially you need to keep track of the references. What's typically done is in Scala C is that the SBT, or nowadays we have actually generalized that to other build tools as well. There's a compiler phase that extracts the references. So to say, well, while we compiled this module, those are the things we touch. So if any of these things changes, then you have to recompile. But that's not done. So what this thing gives you is to say, well, once you track the references, you can actually keep essentially the whole compiler in memory, and you can just recompile. You don't need to essentially read these things from disk anymore, things like that, because we can sort of seamlessly move things over to new runs and essentially keep a consistent because all the references are consistent. My reference just says, well, it's this name and this prefix, whatever its denotation is. If its denotation changes because somebody edited it, or maybe the transitive recompiles that changed the denotation, then we will survive that. So the compiler is essentially has that in its basic architecture to say, well, if it has a new denotation now, there's nothing to invalidate. I will just take that. Everything is just cached.
Okay. And the run ID is roughly identical to the version of the source, or is it?
No, the run ID is essentially on an IDE on every keystroke. I run the compiler again. That gives me a new run ID. So every time I run the compiler again on whatever small subset of files, I get a new run ID.
Even if the source hasn't changed?
Even if the source hasn't changed, yeah. Yeah, you could say it's a transaction ID. Yeah.
So this is along the same lines on a more specific level. Is any of this intermediate information saved off into the class files that are generated so that you can, like, bootstrap the next run with a little bit more information about what's there?
Yeah. So we would need to actually persist only essentially the public API, which is done the typical simple persisting. What we do actually now is much more. We persist the whole tree. So we persist the whole AST because we want to do essentially aggressive inlining and fusion and things like that.
That makes sense.
How much have you thought about parallelizing to speed it up? Because I mean, it's nice and it's functional, but you can imagine a lot of synchronization and coordination issues in non-local pieces of tree whose results would interfere. And
We haven't. We haven't gone very far yet on this one. So I think some of the backend phases can be run in parallel if you want to. The tricky bit of parallelizing is essentially similar to exploring in a chess program because essentially you have a lot of lazy computations and you either have to synchronize them to say, well, somebody's already looking at that, you shouldn't recompute this again. Exactly, yeah. It's sort of the same thing. The other observation is these things are really extremely memory bound. So that means parallelization doesn't necessarily buy you a lot. So
yeah, that's been next.
Yeah. It was one thing I looked a while ago. We looked at Scala C performance with Kirk Pepperdine, who's a performance specialist, and said, "Oh wow, this is cool. You're using all 4 cores. It parallelizes very nicely." I had to say, "Well, actually, that's the GC and the JIT." Yeah.
So as far as fusing the stages go, so you can only fuse those that can otherwise be reordered with respect to each other, right? So they have to be independent in order to be fused.
Yes, each phase can essentially have preconditions that it has to run after another phase or after a group of phases. So that you can't, like, they're not arbitrarily reorderable, but you have a lot of freedom to. Yeah.
Is there a requirement that they need to be independent of one another? Because I would think that if you're having immutable trees that you rewrite, then they cannot observe. If they were serialized, right, they would only be able to observe each other's tree after they ran.
Yeah. So there's a scheme where you say all these transformations are done bottom up. So essentially, for every subtree, you apply all the phases in a group, and then you go to the parent node and you apply all the phases again, and that gives you a certain restriction on essentially where the information can flow. So if you need like context-dependent information from earlier phases, then you need to run in a different group.
Right.
Yeah.
This kind of bottom-up rewriting is what typically also comes up as a problem with parallelization.
Yes.
Martin, I have to ask you.
Yeah.
I'm having trouble with the logic of denotation versus type. I don't see what the separation is between denotations and types. It looks like a denotation is just a post-processed type.
So.
I really want to ask you, since we've got you here, what's a type?
A type is what the compiler knows about an entity such as a tree. So
That's why I think it's a denotation too.
a denotation is well, a type, the difference is really in terms of lifespans. A type is immutable, so it lives forever. So you say that tree, which is immutable, has this type, and that answer must be immutable, so valid forever. Whereas a denotation is something that can change according to the current state of your database, according to the context. So if we look at, let me just go at this one again. If we look at the, where do we have the, oops. Okay, so now we're getting there. So that's a type. So the type just says, well, if I have a selection, let's say, then I have a prefix, which is a type, and I have a name. That's all I have. So the type tells me that, and that's the only thing that's immutable. That's the only thing that would be valid for all periods. Whereas then if I ask, well, what does it mean? What does this reference mean? Then that then depends essentially on the current state of your database. So that's time varying, and that's a denotation. So that's the difference. One is time varying, the other is constant. Yes?
Yeah, I was thinking of this approach in one specific case. Now, for example, suppose you have a nest method call, several calls using the same method with the same parameters. No? So the compiler for any one of them will give exactly the same solution for the same type. No? So in this approach, would you just go to the database once you find the first and then apply the same type for all of them, or you will recompute all the time?
So what the compiler knows is whether source files have changed or not. And it will recompute only if the source file had, so essentially it knows that because the interface of the compiler is, well, recompile this source file. So it doesn't actually look at the hash of the source file. If somebody tells the compiler recompile it, it will assume that the source file has changed, because otherwise there would be no good reason for it. So if the source file wasn't touched, then the compiler will not recompute the type of the symbol. It will say, well, nobody told me to recompute that file, so the file must be the same, so the denotation of the symbol is still the same. So that's how that works. So for each denotation, essentially, also for nested symbols, you crawl up the owner chain until you hit the top level symbol, and it says, well, is that still the same one as it was before? If yes, then I can just roll all denotations forward to the new compilation run.
Yeah. But even inside the, let's say even for the first compilation, no, you still don't have any information for that program?
No. The compiler is essentially the only thing that generates these views. We don't persist them.
And do you think that could be at some point?
If with a sufficiently fast compiler, no. You keep these things in memory, and when you turn off the plug, then you recompute them again. I'm not sure whether we should. I think that's an orthogonal question to it.
Okay.
Yeah. Andre, you had a question.
I had a follow-up to John's question. So is that right that the denotation for this name type instance would be like int? So so this may be the cause of
No, well, if it's a type if it's the type int, then yes, it will essentially, the denotation will be the class int. If it's a value like 2, then the denotation, well, no, if we have a name here, let's say n of type int, then the denotation will be, if it's a single symbol, it will say, well, that's the symbol and its type is int.
So the denotation will be the symbol, and then
will be the symbol and the type. So here here we get both the symbol, because there is a single one, but we also get a type, namely it's of type int to int, which is not apparent from the symbol, and the symbol says it's type t to t. So we get the symbol and the type at the current, corresponding to the current prefix.
Yeah, very technical question there. Do you keep the substitutions that put the initial declaration into the final type?
Not as a separate object, but of course you have that type in the denotation, and you can follow the symbol, and you will see that type here. So you have both types, but we don't keep the substitution as a separate object. Yeah. No. Yeah.
How do you use the information from previous stages of the compilation? For example, when you already have the uncarried type, so when do you have to refer to the type before the?
Yeah. Sometimes we need to. It's not super common, but for instance, the backend has to compute Java C signatures. So essentially the Java C generic information. And that's only the Java backend needs to do that. The JavaScript backend doesn't care about these things. So what we do then is we're at phase backend, and the signatures get essentially they get lost during phase erasure. So we actually go back and to say, well, before erasure started, what was its type, and compute the signature for that type. Of course, we could say, I mean, you can always refactor things and say, well, just keep these signatures as essentially compute them before erasure and then sort of string them along, but that would essentially give us more heterogeneous data types to maintain, so we don't do that. So we essentially go back and look at an earlier phase to compute them. Yes?
How do you envision invalidating these caches? Is that sort of when the source code changes, or phases, or you're going to keep all these caches to speed it up, but when do they become invalid?
Well, that's so some of the caches are indexed by essentially validity period, and then, well, if you're outside that period, you invalidate. Others are like the caches that determine whether the symbol is still valid. Essentially, you have to go back and says, well, has anybody asked you to recompile that source file or things like that. But of course, cache invalidation is one of the hardest problems in this whole thing. Yeah. So that there you have to be very careful. Yeah. We have lots of switches because to say turn the caching off, and if we suspect a bug, we turn all the caches off. But actually, lately we didn't find that bugs were resolved that way. So the caches, it wasn't the cache's fault that bad things happen.
How do you manage the space used by these caches?
So it's either inherently bounded, like if you take the denotations of a symbol during all the phases, well, you can't have more than, I don't know how many phases change, the type maybe 10, so you can't have more than 10 versions, and then we don't maintain it. Or when we say, well, for instance here, what's the denotation of prefix.f, we actually have a bounded size, LRU of size 8. So to say, well, we get, for a given class prefix, we get essentially 8 member denotations, the eight last times we asked a member on that class, we get that thing. So there it's inherently bounded, because otherwise it would grow very large. Any other questions?
So I'm also trying to put together this split between type being immutable and denotation being mutable. So just following on what John started saying.
Well, the denotation is not mutable, it's time varying. The denotation value is also immutable, but a type can have many denotations. So the link from a type to a denotation is mutable in a sense. Yeah.
So if in a program you have a value of declaration and you change it from being an int to being a double.
Mm-hmm.
So instead of val I equals 2, I have val I equals 3.42.
Okay.
Then wouldn't that actually change the type at that point?
Of course, yeah.
So you're doing it in an IDE.
So the type of I just says it's the I in this class. It's the member I of this class. And then you say, well, what's the denotation? Then you say, well, here's the symbol and here's the symbol's type, or seen from where, what my prefix is. So there are two different types. There's a type that just says it's I. And there's the other type which says, well, actually, the I is an int. And that second link can change over time. Yeah.
So basically the type will basically always be a symbolic reference.
Exactly. So you think a type is just what you write. It's nothing, there's no hidden meaning behind it. Yeah.
All right, thanks. That clarifies it.
Okay, cool. Good. Thank you then.